Right. Good morning or afternoon or evening or whenever you're watching this. If you were to watch these in what I think is the proper sequence, this is the first video of week 5. And what I want to talk about here are how you go about getting closer to the exact functional. We don't have it. I think it's fair to say, certainly in my lifetime, we're never going to have it. But there are different ways of trying to approach it, all of which will add new information to the local density approximation. But we'll do it with different philosophies, and that's what I want to show you here. So how would you approach the exact function? You could do it systematically, and that's what Jacob's ladder's approach is going to do. It uses intuition, exact conditions, and known limits. So what we know about the whole, for example. Alternatively, you could say, look, I don't care about any of this stuff. I'm just going to take a bunch of experimental or good theoretical data. I'm going to assume a bunch of terms, and I'm going to fit it to death. And of course, the extreme on that, not to be pejorative, is machine learning. You just throw in a bunch of data, and the machine somehow massages and finds for you connections that you wouldn't have known about. And we'll come back to fitting to death next week. We're not going to do any machine learning, although there is machine learning work that's going on. This week, we're going to talk about systematics. So what do we know? If you read Koch and Holthausen, they're pretty pessimistic about the systematic approaches will get you the right answer. And I understand that. There's, it's like you have a tarp that's 7 miles around, and you could pin it down at about 12 places, and then the tarp can assume any configuration it wants in the middle. That's a little like the functional. We can pin it down in a few places, but how much does that really limit or determine what we get? On the other hand, I think we're going to see that some of these systematic approaches seem to give pretty good results. So I'm a little less pessimistic than they are. So what we know is we know the properties of the whole. You've read a little bit about adiabatic connection and the addition of the correlation energy for kinetic energy. So we add that to EXC. And everything starts with the local density approximation, which turns out to be not terrible. So let's talk about LSD or LDA, local density approximation. This will come up a lot of times this week. You can see this picture a million times, but it's actually pretty useful. How does local density approximation calculate EXC? It takes the density at a given point and multiplies it to the exchange correlation energy at that point per density. So what is it going to do? I'm going to find a density right here, and I'm going to calculate EXC, which if it's just exchange is rho to the 1/3. I'm going to put it in here, and I'll multiply by the density, and I'll multiply by a little volume element. I'll do that again over here, and I'll just keep doing that. And that adds up to EXC. Now, what else might be important? I mean, let's take a look at this. This density, you can see the contour lines. They're different here than here than here. Certainly the density is higher near the nucleus than not near the nucleus. So, and it sticks out here. Clearly the density is going to be a little higher there. Just saying that a given density gives you a given exchange correlation energy density seems like a stretch. So what else might be important? Well, the rate of change of the density with position, and that's going to be taken up by the gradient expansion approximation, which we will soon throw out, and you look at the generalized gradient approximation. The curvature of rho, so the second derivative, and this is starting to feel like a Taylor's expansion, and it ought to. These are called meta-GGAs. You might put an exact exchange. We know to do that. We have cone-sham orbitals. We calculate them just like Hartree 5. And one of the things it does is remove the self-exchange interaction. These are called hybrid or hyper GGAs. And then finally, you can put in wave function-like correlation, excitations, and you get exact partial. So, this is sort of the build-up here. Now, I apologize, I took these photos, they're not the greatest, but here we go. So this is from a book by a gentleman named Tsuneda, and he's thought a lot about orbital energies and density functional theory. But it's kind of a nice picture. It shows you the sort of the family of sorts of density functionals that you might have. So here's LDA, and then encompassing it, taking into account LDA plus is GGAs, so they depend on density and the gradient of the density. Here are hybrid GGAs, so they depend on density, gradient of the density, and Hartree-Fock exchange. Here are so-called meta GGAs that depend on the density, gradient of density, and this is a kinetic energy-like term, which is a second derivative. And there are functionals out here that take into account all of those things, but they have been fitted based on sort of a well-defined procedure. And then there are so-called semi-empirical functions. They use all those terms and were just fit to experimental data. And, they work well. It's not that that's a bad thing. All right, so how do you make sense of all of this stuff? Well, the Purdue group, so John Purdue was a real leader in developing developing functionals, said the following. You can think about the approach to the exact functional as starting with LDA, adding gradient terms, adding curvature terms, adding hybrids, and then adding wave function like correlation, and you move in that direction. And that, that's a systematic way of doing things. In the end, all these pieces are fit together rather than separately. But each adds more what we call non-local information. The gradient squared of rho, we call semi-local. That is, it's trying to give you information about how the gradient is changing, but it does it at a point, like a Taylor series. Exchange is fully non-local. Wave function correlation is fully non-local. And by extending the region of variation of rho, perhaps you get more information about how EXC might vary. Oops, too far ahead. So the philosophies people use in general are, and this would be the sort of Jacob's ladder approach, they're determined by limiting equations. So LDA for small variation, bounds on EXC, limits at low and high density, and you get functionals like PBE Sol, and Purdue-Wang 91. On the other hand, you take parameters and fit to a known experimental set of data, and that was really what was done for V3-LIP and M06, and you get good functions. Are we there yet? So, and that turns out to be a good question. No, the functional is not exact. But I think by the time your projects are done, we're going to see you can do a lot of chemistry pretty accurately. And maybe that's where we're going to live for a while. So with that, I will end this, and the next thing will be on LDA.